All right, this is Mr. Jern, and I'm going to talk to you about AP Physics 1, Workbook 1D. Velocity is a vector! Exclamation point. All right, in this scenario, Angela and Blake are running toward each other from 15 meters away. So you could see some similarities to previous workbook pages with the 15 meters. At time equals t equals 0, at time t equals 0, Angela runs to the right at 5 meters per second, and Blake runs to the left at 3 meters per second. Okay, I'm just going to point out a couple things here. Remember, read the scenario completely. One thing you might want to do is maybe underline or note important words such as the direction that they're traveling or what have you. So, because direction matters. That's why there's a whole word called vectors, because the direction it matters, okay? So using representations, remember what I said a couple videos ago is you're going to have to represent things that are happening, represent phenomena in various ways, mathematically, visually, graphically. So in this case, we have a data table here, and we're going to represent their motion with this data table. And it's got a bunch of times, and it's got Angela's position and Blake's position. Now, how do you know what numbers to even put there? Well, at time equals 0, where are they? They're starting at their respective locations. So Angela is starting at 0, and Blake is starting at 15, okay? Meters. Okay, and you notice that you don't have to put the meters because they are already included in the title for the data table. You should always do that. Put the unit in the data table at the top in the header of the column. That way you don't have to, I guess, clutter the data table with letters and numbers. You just have numbers. Then it says up above that, where's my pointer? There we are. Angela runs to the right at 5 meters per second. That means that for every second that goes by, Angela's going to basically move 5 meters. So that's why it goes from 0, and then at 1 second it's 5 meters, and then 10 meters, and then 15. Every second that goes by, she moves 5 more meters. Blake is moving 3 meters per second, but he's moving to the left starting at 15. So he basically loses 3 meters every second. So 15 minus 3 is 12, and then 9, and then 6. Okay, so remember the position is just a representation. We decided that Angela is starting at 0. Okay, you decide that, and then the powerful part about that is then boom, we all agree that Angela is at 0 and Blake is at 15 meters. Now we could talk about this, okay? Instead of saying one's moving to the right, one's moving to the left, I mean, from whose perspective? Not Angela's, not Blake's, right? They're moving toward each other. Maybe you could say moving north and south. Okay, well, whatever. Those are all good things to say, and this is another way to represent their direction. Okay, make each graph a different color and include a key. Okay, so if you don't have a different color, you can make one solid and one dotted or some other way to represent the fact that they're different. In this case, I've got blue and I've got red, and Angela is red, Blake is blue. And we graphed it. So make sure you start with, like, these are ordered pairs, okay? Time is on the x-axis, so that's gonna be your x value for both people. And you just graph it, okay? You can see the solid colored dots are plotted points. Then we drew the best fit line, okay? Now, it just so happens that we connected the dots, but remember, experimentally gained data is probably gonna be slightly flawed due to error. And so they might not perfectly line up, and you should still, if it's a linear relationship, you should draw the best fit straight line. If it's a curved relationship, then draw a best fit curved line, right? So just you draw the best fit line with the data you've got. In this case, it's given to you, like, this is the very beginning, so the data is going to be like super easy and to work with. So it works out really well. Now, part B, calculate the slope of the line you drew in part A for Angela by choosing 2 points on the line and filling in the equation below. So Angela was red, so we chose these 2 points. I said this in the earlier one, I would have chosen 0, 0, but since it's actually a data point, I don't know if I would use that. It's fine. It's fine. In this case, just pick 2 points and find the slope. Now, remember, always show your work. Don't just plug things into the calculator, okay? Show your work on how you got that. Also, include the units for your answer, 5 meters per second. Where did those meters per second come from? Well, it's slope, right? So it's going to be the units of y, meters, divided by the units of x, seconds, meters per second. Then we do the same thing for Blake by choosing 2 points. So that's blue. Blake is blue over here. And when you get that, you get a negative slope, -3 meters per second. And you might notice, hey, 5 and 3, those are the same values that we had that were given to us. Okay, but now we kind of have an implied +5, and so +5 and a -3. Now we have these as vectors. That positive is the direction. Angela is moving in the positive direction as defined in our number line. Blake got a -3 because he's moving in the negative direction. Okay, so we've got our mud, we've got our magnitude, how much, we've got our units, meters per second, and we've got our direction. Those are the negatives and positives, and those are present for every single vector that we deal with. Okay, in fact, like I said, those are called vectors. Okay, we flip it around. Part D, it says based on the slopes you calculated in part B and C, sketch a velocity versus time graph for Angela and Blake. Make each graph a different color and include a key. So once again, Angela is red, Blake is blue. Angela's slope was +5, and the slope is constant the entire time. It doesn't change the entire time. That's important. So it seems like a strange graph to make, but the velocity at every second is 5 meters per second. And so we have this straight horizontal line to represent the fact that her speed does not change. And we got that from the slope. Then we did that for Blake. Blake was -3 the entire time. His slope of his motion was also constant, so it's going to stay at -3. Carlos, part E, makes the following claim about the intersection points of the 2 lines in the position versus time graph in part A. So remember what I said earlier about reading each question carefully. You got to make sure you answer the question that's being asked, not the question that you might accidentally assume is being asked, because sometimes students will read this and they'll just assume it was the most recent graph. Okay, that wouldn't work out, but here we go. Part A. So the point on position versus time graph where the 2 lines cross represents the time when Angela and Blake are at the same position and traveling at the same velocity. I'm going to scroll back up there just to show what they're talking about. So they're talking about where the X meets. Let me just pick a different color here. They're talking about this, this intersection right here. All right. Now, Carlos, I think it was Carlos, is partially correct. All right, and I'm going to go through this in a second. But right here, it's a position versus time graph. Their positions at this point, just before 2 seconds, their positions are the same, okay? But their speed is not. For a position versus time graph, the slope of the line is their speed. And so their slopes of their graphs are completely different still. So their speeds are not going to be the same. And so that's why they get the answer here, Carlos. The claim is, you would say this, I agree that the position is the same because Angela and Blake do have the same position of 9.5 meters at just before 2 seconds, 1.9 seconds. However, I do not agree that they have the same velocity because the slope of one line is 5 meters per second and the slope of the other line is -3 meters per second. So that is just, again, how you read and represent, you read position time graphs and represent motion with these. All right, let me put that back up there.